Hello everyone and welcome back to my channel. I am Sahil Sawant and I am currently pursuing my MTech from Computer Engineering at VJTI Mumbai. I have strong background in electronics and telecommunication engineering and research experience in RF systems and radio astronomy. Over the past 11 episodes, we have explored how signal processing is from first principles to the real world applications. We started with a simple idea, that is, how a signal is variation that carries certain information. And step by step, we build the tools needed to extract this information. Today, we bring everything together. Today's goal is understanding the complete signal processing pipeline, from the raw measurements to the insights. Now, the first step is about signal acquisition. Everything begins from the measurement, like microphone recording the sound, or let's say an antenna capturing RF energy, or let's say sensors measuring the vibration, or telescopes detecting cosmic radiations. At this stage, the signal is going to be continuous, weak, and it might be mixed with noise as well. Then we will digitize it. Sampling converts physical variation into numbers. This is where Nyquist becomes critical. Incorrect sampling means incorrect reality. Acquisition is what will define the data's quality. Now moving on to the second step, that is about pre-processing. Raw signals are always messy, so we are going to prepare them. Pre-processing includes removing DC offset, normalization, applying anti-aliasing filters, and basic noise reduction techniques like averaging. This step ensures that later analysis is going to be meaningful. Now, the third step is going to be about transformation. Once the data is prepared, we reveal the hidden structure. We are going to apply Fourier transform to represent the frequency content. Then we will also apply spectrogram to get the time and frequency evolution. We also studied wavelets which would define transit detection. Transformation does not change the signal. It changes the perspective of how we observe the signal. Different representations might reveal different truths as well. Now moving on to the fourth step, that is system interaction, filtering and convolution. Real signals pass through the systems and filters are the things that shape the signal. Convolution explains that shape. Here we are going to remove the noise, then we isolate the bands, then we are going to enhance the features. Engineering decisions happen here only, FIRs and IIRs. Then we also looked at how window size is going to matter. We also looked at how bandwidth selection is going to perceive how we look at the signal. This step determines what information is going to be surviving in the next steps. Moving on the fifth step, that is feature extraction. After transformation and filtering out, we extract meaningful qualities. Like for example, we can get dominant frequencies, or let's say any energy distribution or periodicity of the signal. We can even capture transient event and statistical properties of that signal. This is the point where signals become data. We move on from waveform to the parameters. This step fits the machine learning algorithms or control systems and even the scientific analysis procedures. The sixth step is about interpretation of the data that is acquired from the signal now. Numbers alone are not the insights. Interpretation converts signal features into real phenomena. Examples of interpretation may be like if there is a frequency peak, that means rotating machinery fault, or let's say there is a spectrogram pattern, that means it is a speech phenomena. If there is a periodic pulse, it means in radio astronomy that we have captured a pulsar. If there is a burst structure, that means it is a solar activity. Now, signal processing ends with an understanding. No plots, just understanding. Let's summarize the pipeline in short. The first is that we acquire the signal. Second is that we sample the signal correctly. In the third, we clean and pre-process the signal. In the fourth, we transform the representation of the signal. In the fifth, we apply filter and give it a certain shape. In the sixth, we extract the features from the signal, That is, we convert the signal into a readable data. In the seventh, we interpret the meaning of the data the signal has been converted into. This pipeline appears in communication systems or biomedical devices or radars or audio engineering, even in radio astronomy and AI systems as well. It has different fields but same logic. What this series really teaches is not DSP, that is the formulas. It teaches the thinking process that is involved in DSP. Signal processing is observing carefully, handling the uncertainties, choosing the right representations, and making certain trade offs, extracting truth from an imperfect data. The mindset is going to apply everywhere. If you remember one thing from this entire series, let it be that engineering is the art of turning measurements into understanding. Signals are the raw realities. Signal processing is the interpretation of these realities. And insight is the goal of these realities. Now, this was everything about signals and stars, from voltage variations to cosmic discoveries. If you continue exploring signal processing, you will notice one thing: the world is full of signals, and engineers are the one who learn and listen to it. Thank you for being with this journey. Thank you for being a part of my family. That is all about signals and stars.